All right, so if you're coming from the second part of this video series, this is going to be the third and final part where we're going to be doing factor analysis and uh, interpreting the results of this whole do file. So if you came from the second part of this video, you should have your do file replaced with all of your items. So without further ado, we're just going to run these lines. So we're just going to highlight all this and click run. So it should be factor, all your items, and then we want to look at a scree plot, and I'll explain that in just a second. So right after you've run that, you should be able to find this huge factor matrix, and then a graph should pop out. What the heck is a scree plot? Well, scree refers to a geologic term. It refers to the buildup of rocks that accumulates at the edge of a cliff. And so theoretically, what it should look like is like this perfect elbow shape. So it's just like a steep drop and then a tapering off. So this is actually what we're going to be using to determine how many factors are in our test. So how are we going to do that? So there are two ways to do that. One way is to just look at the elbow, and from there we just look at, okay, there's probably two or three factors. Here's an example of what I mean. As you can see, this scree plot, there is one factor that has an eigenvalue of almost 6, and then it's a steep drop to 2 and 3, and then after that, it just tapers off. Because of this, I would say that this test, or whatever this is measuring, or whatever this is a scree plot of, has probably 3 factors. Because you have one factor that is huge, it tapers off into two other factors that are pretty similar in eigenvalue. Now, another way to do this is by looking at the actual eigenvalues itself and making a decision from there. The reason why they do this is because not all scree plots are made equal. Not all of them are going to look like an actual scree plot. Like this is a really clean elbow here. My scree plot, um, as you can see, is pretty curved, right? And kind of jagged at this point. So because there's no definite elbow in my graph, I'm going to use the criterion of an eigenvalue being greater than 1. The reason why we do this is because if we use the criterion of an eigenvalue being greater than 1, we're only accounting for variables that are accounting for as much variance as themselves. So in this case, I'm going to look at which points are above the 1 line here, and I have 4. So I'm going to assume there's 4 factors in my test. All right, so now that we have that, we're going to rerun our factor analysis, but taking into consideration how many factors we've extracted. So factor all of our items, and then at the end here, we're going to put factor the number of items, in my case 4, and just leave the blanks alone. It's going to be 0.4. So we're going to highlight that, click on it, and we should have a new eigenvalue table and a factor matrix. Okay, so for this rotation, you don't have to worry about that. I'm not really sure what that is, but all you need for your factor analysis is these 2 lines right here. So let's take more of a look at these tables here. So this is an eigenvalue table. Now, as you can see here, there are 4 factors that have an eigenvalue greater than 1. What an eigenvalue is in this case, it's a term used a lot in matrix algebra, but what we see here is that eigenvalues denote the proportion of variance that's accounted for by a specific factor. So if you were to actually divide 3.38751 by the sum of all of these numbers right here, you would get 0.4252, or 42.52% of the variance accounted for by this single factor. And as you can see here, it's all accumulating here. So this proportion plus this proportion is 0.64, plus that is 0.8, and then 0.94. So if you were to actually look at the cumulative, my factor structure accounts for 94.64% of the variance found within my test, which is actually really good, right? Because you want to have a model that accounts for as much variance as possible, if you remember that from your lectures. Okay, so in your lab lectures, they will tell you more about what you need to copy from this, but just keep in mind that this is a table that you should keep in mind, that you should um, probably take a screenshot of, is what I was trying to say. Now, time for the factor matrix. What you can see here is a bunch of blanks and numbers. These are what we call factor loadings. Now, factor loadings are essentially correlation coefficients between an item and a factor. So in this case, we see that there are really big loaders onto factor 1, factor 2, factor 3, and factor 4. So as we can see here, item 1 correlates pretty well with factor 1 with a correlation coefficient of 0.4208, item 3 with 0.43, and so on and so forth. Now, one thing that you're probably wondering is, how do we determine what these factors are? Well, that's a good question. What is the usual convention of naming these factors or determining what they measure is by looking at the highest loaders, looking at what those loading items measure, and naming your measure after those items. So in my case, I'm going to look at item 15 and item 12 because those have the highest correlation coefficients. I'm going to look at what they measure. So I'm going to look at what item 12 and what item 15 measures, and then I'm going to name my factor after that. I'm going to do the same process with factor 2, except in this case, I'm going to be using item 4 and item 2 because still negative 0.49 is still the biggest, right? And so on and so forth. Hopefully that makes sense. If not, please consult with your TA on how to name your factors. When you are, what was I trying to say? So when you're trying to remake this table into your results section, what you're going to do is you're going to copy this, you're just going to replace this with item, then just item 1, item 2, up to item 20. Then you're just going to replace this with factor 1, factor 2, factor 3, factor 4, and you're pretty much just going to cut this part out. You don't have to worry about this uniqueness. But you're going to be expected to completely fill out these blank spots. What we're going to fill that out with is going to be a little tricky. So if you actually look around, these numbers are the exact same as these numbers, right? So if you were to actually cut off factor 5 to 11 and just look at these 4 factors, these actually are the exact same numbers as these, except what they're doing is they're just sifting through the items and making sure that they only retain items that are loading onto the factor really well. So what you're going to do when you make the table for this is you're going to make the table, put all these values in, and make sure you put a star right next to them. That way you know that your reader can tell, oh, item 1, item 3, item 5, 6, so on and so forth. Those are the biggest loaders in factor 1. And then they could do the same with factor 2. And you replace the blanks with the corresponding correlation coefficients found within this table. Again, hopefully that makes sense. If not, consult with your TA on how to fill that out. So now that we've done with our factor analysis, what we're actually going to do is going to go back to the very beginning of the stu file and look at what the results actually mean. So I'm going to rerun my correlation matrix. And the reason why we do this correlation matrix is because we want to look at the linear relationships between the items in our test. Because if they're all correlating with each other really well, that means that we can assume that they are all measuring the same thing. And so how we're going to interpret our correlation coefficient is just by looking at the number of correlations that are significant and comparing that to the total number of correlations. So let's say, for example, none of your correlations are significant. That means that your items are kind of measuring different things. And so your test is kind of all over the place. And in that sense, it's not very reliable. On the other hand, another way we're going to be measuring reliability is by looking at the Cronbach's alpha. So I'm going to run this again, and we're just looking at this table right here. Now, the convention that you use to describe your test's reliability is going to be outlined in your lab lectures. So keep note of that. But in my case, I would say that my test has acceptable reliability because it actually falls between 0.7 and 0.8. So if instead of 0.76, it was 0.86, I would actually say that my test has good reliability. And if instead of 0.76, it had 0.96, I would say that my test has excellent reliability due to this coefficient. So that's how you interpret your Cronbach's alpha as well as your correlation matrix. And that should be all for interpreting your results. And that actually should mark the end of this little series. Uh, if you enjoyed it, um, good for you, I guess. I'm not really sure what. I'm not going to tell you to, smash that like button or press subscribe. But hopefully this was really helpful. Hopefully this was helpful for you guys, for those who are kind of struggling to run your statistical analyses. And yeah, thanks for watching.